Hello, welcome and Happy New Year. This is our January 2023 edition of cool, compact OSADL online lectures, and well, this time we have the topic Make Linux Better and Faster with PAPI and Perf. My name is Altenberg and I do have the pleasure to introduce you to the wonderful world of the Performance API and the Perf tools. We start our journey with looking into a few basics. And to understand specifically the history of the Linux Perf tools, we need to look a bit into the evolvement of hardware. And what happened to CPUs, like over the last years, they've been equipped with new functionality, and this also includes performance analysis of your systems. Nowadays, CPUs usually do come with a so-called performance monitoring unit, so-called PMU. The PMU provides a very special set of registers, or specifically counters, that can directly give you the number of specific hardware events like cycles, instructions, or mispredicted branches. So you can, and that's pretty nice, you can actually get performance data actually out of the hardware, which is pretty much non-intrusive for your software. And we all know Linux always adjusted pretty fast to new technologies, and this also happened for hardware performance counters. And as a reaction to CPUs coming with this type of counters, the Perf tools have been developed. This began with a special subsystem in the Linux kernel, just to provide access to the performance counters. This was pretty much all this subsystem could do. But over the years, this subsystem got extended in several areas. So nowadays, you can pretty much profile and trace everything from the application over the kernel down to the hardware. And this is pretty interesting because when you start performance monitoring, you usually come with a high-level view. You see, well, what is the issue or where performance is lost? Like you look at the amount of cycles that have been spent, and then you start zooming in, trying to find the root cause or trying to find the culprit who might be causing a performance issue. And therefore, it's pretty nice to have a tool that can cover everything under one umbrella. Just to give you an overview what this basically means. So the Perf tool is, as I mentioned, using a Linux kernel subsystem. We call it Perf event in this graphics right here. And this gives you a pretty much unified access to several areas of your system. First of all, this can give you access to the hardware. So it gives you access to the performance counters available in the CPU. It can give you access to software events that are pretty much operating system specific, like CPU migrations of tasks or the number of context switches. And it can also give you access to the Linux tracing infrastructure. So you could pretty much use all trace points that are distributed all over the systems, and it can also give you access to K probes and U probes. So that also means that you can have access to dynamic events all over the kernel with one single interface. So you do not have to use all this to collect this data with separate tools. So you have one umbrella tool that can aggregate and report everything for you. Just to match this a bit to the usage of the Perf tool, so one command you can use with Perf, so we'll dig into that over the next few slides. One command with Perf is perf list. That will give you an overview of the events that you can look into, count and collect with Perf. And before you get started, I think that this is what I pretty much recommend to get an overview on Perf. Just hit perf list and count how many events you get access to, you will be impressed. It's quite a lot. It's not like 10 or 20 or 100. It's a couple of thousand events that you could look into, once again, just with a single tool. So here you can see with Perf, you could look into like branch instructions, branches, branch misses, which are hardware events. Here we can see the software events and events that are related to the tracing infrastructure. Well, before we can make use of that, we need Perf available on our system. And Perf is pretty closely connected to the Linux kernel. So therefore, you usually have to build it for a specific kernel version. It's easy to get it because Perf is part of the Linux kernel. As you might already know, so the kernel sources do not only bring the kernel functionality, the kernel sources also bring a couple of tools for testing or example, or even just already production-ready tools that you can really use for your system and that are pretty much closely connected to the kernel. All these tools stay within the tools directory. So to build Perf for your system, just go to Tools Perf, and at the end of the day, if you would just build it natively, the only thing you would need to do is to type make and make install. Since we come with a background where we usually do embedded development and we are like doing cross development for a specific target, I just wanted to put here an example how you could cross compile Perf. So all the examples that I will present over this session, all the tests have been done on a IMX8. So this would basically the example to build Perf for ARM 64-bit. When you build Perf on your own, the important thing is that you double check the dependencies. So Perf is pretty flexible. So if you just cross compile it, that works. So everything that a cross tool chain brings, this is the bare minimum that Perf would need, and the minimum subset of Perf is fair enough to use. You can do already quite a lot with it. But still, it is worth to check which dependencies are available with your toolchain or native on your system. So the thing is that usually when you build Perf, you get a very nice overview, which dependencies are available, but it's hard to get the information to which functionality of Perf this is really related. So for all these missing dependencies, some sub-functionality of Perf might be missing, but like the build system doesn't really tell you which functions are missing. So a very nice example is if you look into libelf. Well, first of all, we might not have any idea why we would need libelf, and this is actually needed for the perf probe command. We will learn about this later in the presentation. So if we do not have libelf, the perf probe command is missing, so it's highly recommended to build perf against libelf. So my basic recommendation is, the more dependencies you get, the harder cross-compiling gets from experience. So what I always recommend is that if you have the possibility, please try to build perf natively and only use cross-compilation when you really need it. Now we have built perf for our target platform. In the next step, we need to configure the system properly. And when we want to use perf, we have to have in mind that the access to related operations might be limited to privileged processes. So at the end of the day, we either need to be root or our process needs specific capabilities like cap perfmon, cap sys ptrace, or cap sysadmin. If I'm neither root or if my process doesn't have these capabilities, well, the system administrator can grant me access to this functionality with the perf event paranoid setting, which is accessible via procfs. Well, on this slide we can see the default setting on a standard Fedora system, which brings number of 2. But what does this mean? Well, For security reasons, you can put several restrictions on how you can collect data with perf. So if you write -1 to this file, this is the least restrictive and the most insecure way to configure the system, but which would be fair enough for a development system. You just need to remove that for a release system. So this is fair enough for a development system. If you write -1, you do not have any restrictions at all. And then with all higher numbers, some restrictions would sum up, which means that if you write 0 or higher right here, raw trace points and ftrace function trace points are excluded. If you write 1 or higher, everything that applies here would apply, and in addition, system-wide performance monitoring is excluded, but you can still monitor user and kernel events. And if you have 2 or higher, this is pretty much similar. So system-wide performance monitoring is excluded, and in addition, you can only trace user events. So it's a pretty fine granular possibility to also set this on your production system, and you need to decide from security perspective what is okay and what not. Well, we have built perf. We know how to configure the system properly. So in the next step, well, let's go ahead and let's use it. And well, as many other commands on Linux, perf is organized in subcommands. So if you just type perf without any argument, perf would tell you about all available subcommands. And I can tell you it's quite a few. And therefore we need to focus in this session on the most important ones. So this will be the subcommands for recording and reporting profiling data. The perf stat command, which is basically giving you counter statistics. We'll have some live view on the system with the perf top command. We'll inject probes with the perf probe command. And I will also look into perftrace, which is a strace inspired tool, but a bit more flexible and way more performant. Well, let's get started with perf and look into a simple example. So if you want to use perf stat, you just type perf stat and then you add the command you want to profile. And perf stat is the most simple command, I would say, from perf. It's just counting events. That's it. It sounds simple, but just by counting events you can already get a lot of information, a lot of performance related information. So if you just hit perf stat without any additional parameter, you would get a default set of events that is being counted. Definitely this would look different for several architectures because hardware counters are different between CPUs, and therefore also the default set would look slightly different here. But from the principle, it's always the same. You have a default set of software events. We've already talked about these: context switches, CPU migrations, or page faults. Then you have a default set of hardware events like cycles, numbers of instructions, or down here like mispredicted branches. And whenever applicable, perf would also derive a couple of metrics out of these numbers. Well, this is already giving us a lot of information. We can also focus on specific numbers. We might be interested in the number of cycles, which looks actually pretty high. Well, let's try to focus on that one. So if we want to count just a specific event, we can use the -e parameter of perf stat, which would just tell, I just want to count the cycles for this specific command. Now looking at the number of cycles right here, we might be interested in which context these cycles are being spent. And this is what we can do with the colon. So if we just type cycles colon k and cycles colon u right here, perf would tell us the cycles that have been spent in the kernel and the number of cycles that have been spent in the userland. So just with this simple extension of the command, we already know where most of the cycles have been spent. And obviously, we spend most of the time in kernel space. And so that's already quite some interesting information. And there's other use cases where you are really interested in which context an event has been counted. Just think about virtualization and hypervisor technologies. So if you are performance monitoring something that is running within the guest, just like counting cycles or context switching, would you also count all the noise from the hypervisor and the host operating system? Well, if you just count the cycles, then yes. You would just count all the cycles that happened during the instruction of a specific command. But there's also a context right here, specifically for virtualized environments. For example, with the hypervisor, you could just see what happened in the specific hypervisor context. And most interestingly, in the virtualized environment with the capital H and the capital G, you could see how many cycles, for example, you spent on the virtualization host or how many cycles you spent within the guest system. And if you just look into the guest, you do not count all the noise from the host operating system. So the PMUs in modern CPUs, they allow this context-specific counting also for hardware. Well, hypervisor and virtualization environment needs to implement this properly. And if it's properly implemented, Perf has the ability to expose it. And once again, for virtualized environment, this is a very interesting functionality because performance profiling with a guest operating system is something pretty common today. Let's make our example a bit more advanced. So with Perf Stat right now, we've looked into a default set of events that we can count. And then in the next step, we just added counting hardware events. Let's add a few more. So we've been starting with hardware events. So we've been counting cycles. We could now also tell, well, in addition to the cycles, I want to see the context switches, which are these software events. And at the same time, I also want to use the tracing infrastructure. So I want to specifically count the so-called get switch event. So this is an event that is generated when a task is getting CPU time. So once again, these events do come from very different areas in the operating system, but we can count it with one simple command. So we just let the system sleep for 2 seconds and we count these events. So we spent about 3 million cycles. We've had 3 context switches and we had 3 get switch event during that recording time. So that already does a lot. Another important use case is that, well, in most of the cases, the events that are already there in the hardware or in the operating system are sufficient. But sometimes when zooming into and you really want to figure out where performance is getting lost, well, you want to debug your own driver or you want to look into areas in the kernel that do not have any specific trace events or not at the specific code portion that you are interested in. So for that purpose, you need the ability to add custom events to the kernel. And this is done with the perf probe command. And once again, remember to have this available, you need to build perf with libf. You can actually add a probe at any point in the kernel mostly. And the syntax is fairly easy. So if I just type perf probe kTimeGet, I will dynamically inject a trace point at the entry of the function kTimeGet. There's many other options. I highly recommend you to read the related documentation. You can also use file name, line number. You could also use function name, function offset, and so on and so on. So this is the most simple use case, just having a trace point at the entry of this function. Perf will then automatically provide a name or define a name for this event. And from that point, we can start count it or recording it. So Perf even prints out a example command, how we can now look into this custom trace point we just added to the kernel. So using the perf-stat command, well, we just use the -e parameter and provide now our custom event that we just dynamically injected to the kernel, and we can start counting it. We can slightly adjust this command. So I've just added right here the -a parameter. And what we can see is that there is now a significant difference. So right here, we just hit that function once. With this command, during the same runtime, we've been sleeping for 1 second. During the same runtime, we've hit the very same function 433 times. So what was the difference here? Well, it's obviously the -a function, and -a means you go for system-wide monitoring. So this is a very important parameter for perf. Usually you just monitor in the context of the process that you are running. So if you want to do system-wide monitoring, you specify the -a parameter. So you really have, once again, many options to zoom in and to zoom out with perf to really get related data when you look into a specific problem. Well, now with perf probe, we got a lot of flexibility in counting specific events. But I promised at the very beginning of the presentation that we can count each and anything from the application down to the hardware. Well, let's go ahead and see how we can count events that are coming from the application. And once again, the perf probe command helps us out here. So the perf probe command cannot just put probes inside the kernel. It can even put a probe at any given point in a application. And the only difference is that you provide the -x parameter to perf probe, then you provide an executable, and it's not necessarily just an application. It can even be a library, and then you provide the offset or the function name where you want to inject the probe. So with this simple example, I just want to see that every time when printf from the C library is being called, I want to be able to count this event. And now it's pretty similar to perf probe for a kernel event. So perf will define a unique name for this event, and then I can start recording it. Let's just look into this with a very simple example. So we have this hello cool program, and obviously we can see we are calling the printf function just 10 times. And now our intention is that we want to count every single call to printf. So we compile and we link our program. And as you can see, there's no modification necessary to count these events, neither in the source code nor when we compile it. I just can compile it, I just link to the standard C library. In the next step, I run the program within perf-stat, and I just tell perf that I want to count the probe-libc printf event. I run the program, and if I look into the statistics, we can see that printf has been called exactly 10 times. Now we get the full thing from the application down to the kernel. We can dynamically inject probes even in the application without recompiling it. So let's map this to our overview. We've added a dynamic event to the kernel on kTimeGet. So at the end of the day, this is done by using kprobes. And we do not have to configure the kprobes manually. Perf does this for us. And the same happens with the user space event, just counting the calls of printf. This is done using uprobes. Well, and also right here, we do not have to configure the uprobes manually. Perf does it for us. And if you have ever configured a uprobe manually, you know it's doable, but there's some effort involved and it's a bit error prone. So it's pretty nice to have a common interface for all these functionality and also get common reporting on all of these numbers. And now when we read right here from the bottom up, we can really see that down from the application, over the kernel with dynamic and static events and just counting scheduling related data down to the hardware, we have access to all relevant data of the system for the purpose of performance monitoring. So far for the perf stat command. So once again, perf stat is about counting events. The next interesting command is perf record. So this is more looking into profiling. So we just take samples while an application is running, and we want to figure out what happened during that time and how the time has been spent. So the syntax is pretty much similar, which means that everything that I showed you for perf stat is available for most of the perf subcommands. So I can also tell to count specific events in addition. So this is just exactly the same events like we did for the uprobe example. We record the data and gets written to a file, and you need to know it is a sampling. So it's sampled by a specific frequency, so you can even provide the frequency via the command line if you are not happy with the number of samples that have been taken. So the data is written to a file, and it can be analyzed with the perf report command. So perf report takes this perf data, it gives us an overview of the number of events that have been counted. But in addition, we also get the overview where the time has been spent and in which context. So this was the process that have been running, and these were in this case, the kernel symbols that were active during this time, and we see the distribution of computation time right here. And the same for the context switches, so we could see where they happened. We can also see the distribution, and we can see the related symbols. So this is way more than just counting. We can really analyze where the time has been spent within the operating system. So this is recording and reporting. Another interesting command when we look into several aspects is perf trace. As you can see from the output, it looks pretty similar to strace, and this is basically the intention. It provides the same functionality like strace, but much more. It is way more flexible, so you can just classically trace system calls, but in addition you can trace any other event and just map it to that view, so you can combine the data. So this is one advantage. The other advantage when using this over the perf subsystem, it's a bit more efficient. So the influence on the application, the timing influence on the application that you are tracing is way less than with strace. So we've now been counting events. We've been recording and reporting events. We've been tracing syscalls. Last but not least, I would like to look into perf top, which is maybe one of the most powerful perf subcommands. So with perf top, you can get live performance data, like the top command, that could tell you how much CPU time is spent by specific processes. Perf top does the same, but on a very different granularity. So on a symbol level, you can really see where currently the time is being spent in your system, and you could actually navigate here, you could zoom into, you can have a live annotation on the assembler code and even the C code that is being called, and it's really a live view in your system. So you would use perf top, for example, if you see the load average is growing in your system and you want to figure out where this load is coming from, then you use perf top and you get a symbol granularity idea of where the time is spent. So just to get you an idea on this, this was an idle system on my IMX8, and well, I decided to run a flood ping on this, which I would expect would cause a very high number of interrupts. So let's see how this reflects in perf top. Well, first of all, on the bottom left, you can see the number of interrupts has significantly increased. So that's what we expected. But we can even see where the time is now being spent. So we can see that the receive function of the Ethernet driver has now significant load. And we can also see that we, in addition to receiving packets, we also spend a measurable amount of time in transmitting packages. So we are just responding to the ICMP requests that are now flooding in. And this is just one simple command, perf top, and we have a live view on symbol level on where we spend the time in the system. And once again, we could even zoom in right here. There's way more we could learn about perf. But I think you already have an idea that it's a very powerful tool, and it's really worth to dig into this a bit more. Well, apart from perf, there's also other useful utilities when it comes to performance monitoring of a system. And one pretty common additional tool that you could use is PAPI, the so-called Performance API. So PAPI is basically a library that provides a consistent interface to hardware performance counters. I mean, this is pretty much the same as we do with perf. But in addition, it provides also access to other methodologies for performance measurements. So you could combine even more data with one single library. Another feature of PAPI is that it's available for multiple operating systems. On Linux, it provides a perf component, so you can also use perf with PAPI, but way more, so we'll dig into that. And there's recent releases, so this is the link where you could download the latest release, and under this link you will also find a link to the Git repository if you want to follow the latest development. Well, let's compare this to perf. So we still know this overview right here, and pretty similar to perf, PAPI will just connect to the perf event subsystem within the Linux kernel. From this point, well, we might ask ourselves, but what's the benefit? Okay, we learned it's available for multiple operating systems. Okay, one advantage. But there's a bit more. First of all, it provides different levels of API. It provides a so-called low level and it provides a so-called high level API. And the high level API is fairly easy to use. So it provides a very easy way to get access from the application to this perf event related data. Another advantage is it also comes with a couple of subcomponents. And actually perf is just a subcomponent of libp-API. You can also use libcuda. You can use LM sensors with PAPI. Like you want to see how the temperature might infect the performance of your system. So you can collect the data with one single measurement and then aggregate it. So that's also pretty important that you can aggregate more data. And well, there's way more. So as of today, there's roughly 35 subcomponents of PAPI with a single abstraction layer. So you can count and aggregate a lot of different events for performance-related analysis of your system. Before you get into PAPI, what you need to do to know, PAPI has a specific definition of events. So we have the so-called native events. These are all the events that can be counted on a specific platform, like perf events or LM sensors or CUDA events or whatever. Then we have the so-called preset events. So these are predefined sets of commonly used events. And now the important thing is with a unique naming scheme. Specifically, hardware events can have different names. So the same metrics can have different names like on x86 or on ARM or on RISC-V. So PAPI gives you a common name for these counters. And these are the preset events. Preset events always map to a native event, but they provide a common naming scheme. And we have the derived events, which are also preset events, but they are not mapped to just one native event. So they are like deriving data from multiple native events. Well, before we can use PAPI, we can build it. So it's based on a classical configure, make, install process. So this is how you would cross-compile it for a IMX8, for example, you need to provide a lot of information, which can be quite error-prone. So it's obvious that the CPU and the sub-architecture is pretty easy to figure out, also the cross toolchain to use, but you can see you need also to provide which wall timer to use, how to handle thread local storage. You need to provide the correct virtual timer. So this is doable, but also here the recommendation would clearly be, if you have the possibility to build PAPI natively, go for a native build and only use cross-compiling if it's really necessary. At the end of the day, it's just configure, make, install, and you have everything what you need ready to use. When we have installed the PAPI, we can easily check which functionality is being available. So I told you it's organized in so-called components, and which components have been built in can be checked with the PAPI component available command. So this will give us a basic idea on our system and then a list of the components that are available. On Linux, the default component that will be always there is the perf event component. If you want to have additional components there, you can adjust that with the configure script, which has a -- with components parameter. Another important command is the command that shows the available preset events. This is an example on the IMX8, and right here with the PAPI L1 ICM, we can see this is the level 1 instruction cache misses. And this is the abstracted name. So this maps to a native event, and this is very different on several architectures, but with this naming scheme, we can use the same code later than on x86 and other platforms, and it would then, the library would make sure that it maps to the correct native event. Right here in the very first line, we can also see a derived event. So the data cache misses. The derived yes here means that this counter is derived from more than one native event. But once again, it's a common naming scheme with the preset events. And it's also roughly, I think, 100 native events are provided by default by libPAPI. Now, how to use it? First of all, let's look into the low-level API. So we have a very simple program. And, well, to use the low-level API, which gets a pretty fine-grained access, so you have a lot of control what happens. You have to do more work, but you really have the control on how things are profiled and traced. So first of all, you always need to initialize the library. And also the library gives you different functions for the error handling. So the API at the end of the day is pretty forward. So first of all, initialize the library. Always make sure that you do the proper error handling. Then in a next step, we need to create a so-called event set. So you remember with perf, we told on the command line which events we really want to count, right? And this is pretty much the same we do here with the API. We need to tell PAPI which events we want to count. And therefore, we need to create an event set. So we create an empty event set. And then we start adding events. So in these simple examples, we just want to count the number of total cycles that have been spent. We make sure that we reset counting. And at any given point in the code, we can start counting. So this would just be hitting enter with the perf start command. Now we start counting. We do some work. So we just have a loop with a predefined number of cycles, 1 million in our case, and we just increment this counter right here to just simulate some load on the system. When we want to stop the measurement, we just need to call PAPI stop, counting stops. We can also reset at any given point to restart counting. So we stop right here. And the final step is, with the low-level API, we are also responsible for the reporting. So we need to print out the results. So this would be the number of total loops we ran. And this is, in the very last line, we see how many cycles have been counted by lib PAPI. So with the lower level API, it's pretty fine-grained access, and we need to make sure that we do the reporting on our own. So how does this look like? So we compile the program. So in the first try, I compiled with optimization level 01, and we link this program to lib PAPI. We execute it, we see, okay, we've got 1 million loops and slightly more than 1 million cycles have been spent in the program. Now let's recompile with another optimization level. Do exactly the same, build the program, link it against lib PAPI, and we can see we still have the 1 million loops, but we spent way less cycles due to the different optimization level. This is a very simple example, but I think it pretty nicely tells you how you can count performance-related data with lib PAPI. And it can be even simpler. For these use cases where you just count common events like the cycles that have been spent, you can even use the high-level API, which has a simplified programming interface. So as you will see, it's way simpler as the low-level API. So you have not that much influence on how the profiling is being done, but it's way simpler. You have flexibility because the event sets are not defined within the code. They are defined in an environment variable. And you do not have to take care about the reporting. This is done automatically. Let's translate the given example to the high-level API. And it's as simple as that. We just need to call PAPI HL region begin. We give a name, a unique name to this measurement. We do the load. It's the same application we used before. And we want to stop the measurement. We just need to call PAPI HL region end with the related name of our measurement. And that's it. That's the only thing we need in the code. So you will agree that this is fairly simple. But how does this work? First of all, following the same example, first of all, we compile with 01, also linking against lib PAPI. And before we run it, we export a variable which is called PAPI underline events. So we tell we want to count the total number of cycles, and we also want to look into the cache events. We run the example, and automatically, when we stop the measurement, the result will be written into a JSON file, which basically looks like this. And you can see that the events we specified here will be in the status report that the high-level API creates for us. Look into the same example compiled with 02. We can actually also see right here that the number of cycles has drastically reduced. So it's exactly the same example, but using a different API. So this should give you an idea of the difference of the low-level and the high-level API of lib PAPI. Well, we are at the end of our journey. So we already learned a lot, and I highly recommend you to do some further reading on these tools because they are really, really powerful and you can do a lot. Let's just briefly sum up on what we learned in this session. So Perf is a tool that offers a wide range of possibilities for profiling and tracing everything from the application down to the hardware. So you can have a high-level view and then you start zooming into the topics you are interested in. One additional tool is PAPI that offers a OS-independent consistent interface to several methodologies for performance measurements and systems analysis like LM sensors, CUDA, and way more, so you can aggregate a lot of data with a very simple API. Both technologies can be used on all major architectures. So on ARM, on x86, on RISC-V, you can use it. And once again, when you build it for both tools, for Perf and PAPI, the clear recommendation is, even though cross-compilation is fairly easy, at least for the minimal feature set, dependencies and settings can get quite complicated. So we recommend always to build natively and only use cross-compiling of these tools when you really need it. So we are at the end of our journey, of our introduction to PAPI and Perf. Thanks a lot for participating in this session. I'll be around for the discussion later on today. I'm already really looking forward to your question. Thanks a lot and talk to you later.